Okay, last bit of relativity. Calculate length contraction and explain the train tunnel paradox. Again, it's a paradox because it's not. Okay, so much like how we have with time dilation, we have length contraction. Similar notation as before. The subscript of 0 means that you observe the thing, the length of the object as you are moving with the object. So that's called the proper length sometimes, even though proper is really dangerous. And then the L without the subscript is going to be the length that is observed from someone who considers themselves stationary and considers the object moving past. Cool. Why is this called length contraction? Because gamma is always greater than 1, which we figured out last time. So L naught will always be bigger than L. So it's always going to get contracted because it starts off big and then when you go to the other frame it contracts, hence the name. So why does this happen in the first place? Well, if we go back to super basic stuff, velocity equals distance over time. Okay, well, we've established that this velocity, if it's the speed of light, which we're now going to make it happen, so we say this is the speed of light. No matter who you are, where you come from, what you're doing, whatever, that's always constant. Well, that means that this divided by this must be constant. But we established last time that how long a duration is depends entirely on your perspective of things. Well, if this is constant and this is not constant, the only way to make that work is if this distance is also not constant and that these two conspire to make this always constant. So that's the basic gist of this. If you allow for time dilation, you necessarily have to have length contraction as well to cancel each other out such that the velocity of light is always the speed of light. Cool. One other little side note is that the contraction happens in whichever direction the object is travelling relative to the other observer. So if we're on Earth and we're watching something travel past us across that way, it will appear shorter in that direction. If we're watching it travel up that way, it will appear shorter in this direction. The other dimensions are not affected. Or the perpendicular dimensions aren't affected. Cool. Alright, so what's this train tunnel paradox? Alright, so I've got 3 scenarios. This first scenario, we've got a train sitting in a tunnel, and it just so happens that this train perfectly fits within that tunnel. Isn't that nice? And from our perspective, both the train and the tunnel are both stationary. So fantastic, we consider them the exact same length. Great. Well, now we're going to look at a slightly different scenario. It's the exact same train, just now the train is travelling at 2/3 the speed of light through this tunnel. Alright, we're sitting stationary relative to the tunnel, so we observe the tunnel to have no velocity. Well, this thing's moving relative to us, so we must see it have some length contraction. Doesn't matter if it's travelling left or right, point being, it gets contracted in the x direction. Well, that means all of a sudden I've got a tiny train. Notice that the height is still the exact same, because that's not the direction of travel. It's just in the direction of travel, you got squished in. Well, that's a bit weird. Well, if we flip that around, if now we're in the train, well, the train has zero velocity as far as we're concerned, but the tunnel, if we're sitting in the train, the tunnel is going to appear to go past us at 2/3 the speed of light. Well, hang on, that means that we would observe the tunnel as being contracted, which means that the tunnel is now shorter than the train. So, which is it? Is it the same? Is the tunnel bigger? Is the train bigger? Again, it's just like asking that question from before, whose clock goes slower? It's a bit of a silly question to ask. Excuse me. It's a bit of a silly question to ask because it depends all on perspectives. All of these conspire, regardless of your perspective, to keep the speed of light constant. So you can end up with a train that's longer than a tunnel, appearing to fit well inside the tunnel if you're travelling, if the train and you are travelling relative to each other at a sufficient velocity. So that's that. Another consequence of this, which has definitely been experimentally verified a million times, is if you have muons firing, is it muons or mesons? Doesn't matter. One of the particles. No, I think it's mesons. Oops. Anyway, doesn't matter. they're particles. They're cosmic rays. They Earth gets showered in them all the time, and these particles have a very short half-life. If you want the particular values, you can look it up, but it's like stupidly short. However, they're traveling stupid quick as well. However, if you take the nominal velocity and you take how far up the atmosphere goes, which depending on which definition of the atmosphere you want, roughly 100 kilometers, you would normally find that, oh, hang on, they should only get so far into the atmosphere before, on average, they'll decay. So we really shouldn't see that many of them on the surface. But it turns out, if you're doing detections, you get heaps of them down at the surface, which is way beyond what you would nominally expect. Well, here's our frame from the people sitting on Earth. So the particles are moving at 95% the speed of light. Earth is not moving relative to us. And the distance from us to the top of the atmosphere is 100 kilometers. So we get this weird thing where, oh, we expect them to go here, but we're detecting them way down here. What's going on? Flip this around to the particles' perspective instead. From the particles' perspective, it's not moving. The Earth is racing up to it at 0.95% the speed of light. Well, okay. Well, if Earth is racing towards it, that means Earth will be contracted in that direction of travel, which means the atmosphere will be contracted. How far will it be contracted? Well, we can figure that out. We can go through, which colour do we want? Go purple gamma equals 1 over root 1 minus the velocity of, or the relative velocity, which is going to be 95% the speed of light. So 0.95 over C, and then all of this guy squared. You can square them each individually, or otherwise it doesn't really matter, it's all multiplicative. Cool, we chuck that into our calculator, and we get whatever we get, 0.95, 0.95 C. That's better, so the C's will cancel. 0.95 square, 1 minus that, 1 divided by that. Did I punch that in right? Probably not. So let's check. Oh, I didn't square root it. Oops. 0.95 square, 1 minus that. Come on. 1 minus that, square root that. Then 1 divide. Gives me roughly, where's my blue? 3.2. Cool. So I've got a gamma of 3.2. Great. Alright. Well, what's going to happen? Well, my gamma is 3.2. Okay. The length of the object in the rest frame, well, the object is the atmosphere. What's at rest relative to the atmosphere? Well, Earth is. And from that perspective, that distance should have been 100 kilometers. So that 100 kilometers is going to get divided by this gamma. So we get, ooh, if we can drop it, 100 divided by 3.2, which gives us whatever it is. 100 divided by this rough 3.2 is roughly 31 and a bit. 31-ish kilometers. So all of a sudden that atmosphere is only 1/3 the distance. And as it turns out, that's a sufficient contraction such that a whole bunch of these particles are now going to reach the surface and you're going to be able to detect them, and that's what length contraction does for you. So with all of this topic, you have to be super careful. Make sure your speed of light is always constant for all observers, and then always consider your time dilation and length contraction. Be super careful about what you're assigning is the proper length or the proper time. But the basic gist is, if you are observing something moving relative to you, the thing that's moving, you will observe its clock ticking slower. And if something is moving relative to you, you will observe its length to be shorter in the direction of travel. So that's basically that. That's 6.3. Email me if you do get stuck with anything. Other than that, cheerio.